The statistician Ronald Fisher explained the concept of hypothesis testing with a story of a lady tasting tea. Here we will consider a similar example based on James Bond, who insisted that martinis should be shaken rather than stirred. Suppose we gave Mr. Bond a series of 16 taste tests, and on each one we asked him to decide whether the martini was shaken or stirred. Let's say Mr. Bond was correct on 13 of the 16 taste tests. Does this prove that Mr. Bond has at least some ability to tell whether the martini was shaken or stirred? This result does not prove that he can tell the difference. It could be he was just lucky and guessed right 13 out of 16 times. But how plausible is the explanation that he was just lucky? To assess its plausibility, we determine the probability that someone who is just guessing would be correct 13 out of 16 times or more. This probability can be computed from the binomial distribution and equals 0.0106. This is a pretty low probability, and therefore someone would have to be very lucky to be correct 13 or more times out of 16 if they were just guessing. So either Mr. Bond was very lucky, or he can tell whether the drink was shaken or stirred. The hypothesis that he was guessing is not proven false, but considerable doubt is cast on it. Therefore, there is strong evidence that Mr. Bond can tell whether a drink was shaken or stirred. We now consider the case study on bias against obese patients. Physicians were sampled randomly, and each was shown a chart of a patient complaining of a migraine headache. They were then asked to estimate how long they would spend with the patient. The charts were identical, except that for half the charts the patient was obese, and for the other half the patient was of average weight. The mean time physicians reported that they would spend with obese patients was 24.7 minutes, as compared to a mean of 31.4 minutes for average weight patients. How might this difference between means have occurred? One possibility is that physicians were influenced by the weight of the patients. On the other hand, perhaps by chance, the physicians who viewed charts of the obese patients tend to see patients for less time than do the other physicians. Random assignment of charts does not ensure that the groups will be equal in all respects other than the chart they viewed. In fact, it is certain the groups differed in many ways by chance. For example, the two groups could not have exactly the same mean age, if measured precisely enough, such as in days. Perhaps a physician's age affects how long he or she sees patients. There are innumerable differences between the groups that could affect how long they view patients. Therefore, it is possible that these chance differences are responsible for the difference in times. To assess the plausibility of the hypothesis that the difference is due to chance, we compute the probability of getting a difference as large or larger than the observed difference of 6.7 minutes if this difference were, in fact, due solely to chance. Using methods presented in a later chapter, this probability can be computed to be 0.0057. Since this is such a low probability, we have confidence that the difference in times is due to the patient's weight and is not due to chance. It is very important to understand precisely what probability values mean. In the James Bond example, the computed probability of 0.0106 is a probability he would be correct on 13 or more taste tests out of 16 if he were just guessing. It is easy to mistake this probability as a probability he cannot tell the difference. This is not at all what it means. The probability of 0.0106 is the probability of a certain outcome, 13 or more out of 16, assuming a certain state of the world. James Bond was only guessing. It is not the probability that a state of the world exists. Although this might seem like a distinction without a difference, consider this example. An animal trainer claims that a trained bird can determine whether or not numbers are evenly divisible by 7. In an experiment assessing this claim, the bird is given a series of 16 test trials. On each trial, a number is displayed on a screen, and the bird pecks at one of two keys to indicate its choice. The numbers are chosen in such a way that the probability of any number being evenly divisible by 7 is 0.50. The bird is correct on 9 of 16 choices. From the binomial distribution, we can compute that the probability that someone only guessing would be correct 9 or more times out of 16 is 0.40. Since a bird who is only guessing would do as well as this trained bird 40% of the time, these data do not provide convincing evidence that the bird has any special ability. As a scientist, you would seriously doubt that it does. Would you conclude that there is a 0.40 probability that the bird can tell whether a number is evenly divisible by 7? Certainly not. You would think the probability is much lower, perhaps lower than 0.0001. To reiterate, the probability value is the probability of an outcome, 9 out of 16 or better, and not the probability of a particular state of nature. The bird can tell whether a number is divisible by 7. In statistics, it is conventional to refer to possible states of nature as hypotheses, since they are hypothesized states of nature. Using this terminology, the probability value is the probability of an outcome given a hypothesis. It is not the probability of the hypothesis given the outcome. This is not to say that we ignore the probability of the hypothesis. If the probability of the outcome given the hypothesis is sufficiently low, we have evidence that the hypothesis is false. However, we do not compute the probability that the hypothesis is false. In the James Bond example, the hypothesis is that he cannot tell the difference between shaken and stirred martinis. The probability value is low, 0.0106, thus providing evidence that this hypothesis is not true. However, we have not computed the probability that he can tell the difference. A branch of statistics called Bayesian statistics provides methods for computing the probabilities of hypotheses. These computations require that one specify the subjective probability of a hypothesis before the data are considered, and therefore are difficult to apply in some contexts. The hypothesis that there is no real effect and that any apparent effect is due to chance is called the null hypothesis. In the physician's reactions example, the null hypothesis is that in the population of physicians, the mean time expected to be spent with obese patients is equal to the mean time expected to be spent with average weight patients. This null hypothesis can be written in two ways, as shown. The null hypothesis in a correlational study of the relationship between high school grades and college grades would typically be that the population correlation is 0. The Greek letter rho is the population correlation and should not be confused with R, the sample correlation. Although the null hypothesis is usually that the value of a parameter is 0, there are occasions on which the null hypothesis is a value other than 0. For example, if one were testing whether a subject differed from chance in their ability to determine whether a flipped coin would come up heads or tails, the null hypothesis would be that pi equals 0.50. Similarly, in the James Bond example, the null hypothesis is that his probability of telling the difference between shaken and stirred is 0.50. Keep in mind that the null hypothesis is typically the opposite of the researcher's hypothesis. In the physician's reaction study, the researchers hypothesized that physicians would expect to spend less time with obese patients. The null hypothesis that the two types of patients are treated identically is put forward with the hope that it can be discredited. If the null hypothesis were true, a difference as large or larger than the sample difference of 6.7 minutes would be very unlikely to occur. Therefore, the researchers rejected the null hypothesis of no difference and concluded that, in the population, physicians intend to spend less time with obese patients. If the null hypothesis is rejected, then the alternative to the null hypothesis, called the alternative hypothesis, is supported. The alternative hypothesis is simply the reverse of the null hypothesis. If the null hypothesis that the population mean for obese patients is equal to the population mean for average weight patients is rejected, then there are two alternatives. 1. The population mean for obese patients is less than the mean for average weight patients, and 2. The population mean for obese patients is greater than the mean for average weight patients. Naturally, the direction of sample means determines which alternative is supported. Some textbooks have argued that rejecting the null hypothesis that two population means are equal does not justify a conclusion about which population mean is larger. However, as is clear from the discussion in the chapter on confidence intervals, this view is incorrect.